Welcome, everybody. I'm your host, David Aguilar. Tonight, here in Cambridge, Massachusetts, we're going to see something absolutely exceptional. In March of 1965, astronaut cosmonaut Alexei Leonov stepped outside of his spacecraft for the very first time to become the first human to do an extravehicular activity outside of a spacecraft. At that moment, his spacesuit became his spaceship. And 10 minutes later, after setting history, he tried to get back into his spacecraft. He couldn't do it because his spacesuit had inflated and it was now bigger than the entryway to his spacecraft. He made it, but it showed that spacesuits and the way they needed to be built differently. They were not like suits we would use underwater. Tonight, we have Dava Newman. She is the Director of Aeronautics and Astronautics and Engineering Systems and Director of Technology and Policy Programs at MIT, and she is going to show us, just possibly, the spaceships of the future. Dava?
It's my great pleasure to be here. Welcome. Welcome to Cambridge. Welcome to Harvard. And I look forward to speaking with you tonight. I'd like to take you on a journey from Earth to Mars, if you'll allow me. I want to kind of put the philosophical view on it in terms of, why go to space? Why go to space for humans? I hear this all the time. Well, for exploration, there's a lot of good reasons. I have my good reasons. But fundamentally, maybe it'll teach us more about life here on Earth. So I have Buckminster Fuller's image of mini Earth up on the top left. And what an idea, what a powerful idea. Put all the world leaders together in one building, and you look outside and you see Earth. And you don't just see Earth, but you see what's happening on Earth. So you see war and famine and hopefully, star-filled beautiful things and sad things, but, we would get it. Maybe we'd make different decisions, for all of our world. As far as I'm concerned, we have one planet that we're living on. And so in all of my exploring via space and sea, and a little bit on Earth, I think it's about the human condition and the human spirit. So that's kind of my pitch for exploration and discovery. I have to give you a little bit of background here. What happens when we go into microgravity, the microgravity environment of space? We're only going to go 400 kilometers, that's 200 miles up to the International Space Station for this first slide. You're going to lose a lot of muscle and bone. And maybe we can knock out the sound for this. It's a little loud, just background noise from my lab. So we're not going to, we might pedal our way to Mars, but these are, of course, on Earth. But I'll draw your attention just here, just to orient ourselves. What happens when we go into the microgravity environment? You're going to lose about 30% of your muscles, 40% strength degradation. That's the good news. The bad news, you're going to lose 1 to 2% bone mineral density per month. Now, who wants to go to the space station for 6 months? The kids, yes, thank you. Okay, so good, it gives me a job. So we want to counter those deleterious physiological effects. I want our astronauts to be really healthy and have muscles and bones that are in shape, kind of 1G shape here, Earth shape. So we have some ideas about that. And here, again, on Earth, we have some suit designs. Kubrick's 2001 Space Odyssey, still one of my favorites, but I realize now the younger generation has never seen it. Did see it. Is a 2 kilometer long spinning spacecraft, and you're going to be kind of walking on the walls, if you were. They wouldn't feel like the walls because it would feel like the floor. That's artificial gravity, kind of on steroids. Engineers love it, like me, but it's expensive. So in our lab, we do this short arm centrifugation that you saw in the video, just 2 meters. And if I spin you, then I can kind of recreate gravity. It's really an acceleration field. Feel 1G, 1 gravity back at your feet, because that helps us counter this musculoskeletal loss. So here you see our skeleton. Bone is actually a complicated organ. How am I doing? Oh, thank you. My microphone's on the back of my dress here, so hopefully you can hear me. So anyhow, here's the bone loss we were talking about, and it doesn't stop. So I had 1 volunteer for space station, and but now our Mars mission, that's about 4 years. It's about a 6-month trip out and about a year and a half back home because orbital mechanics is going to dictate we probably want to take the short leg out. And we're going to go to Mars and we're going to be on the surface for 600 days. Why? To look for the evidence of past life. It might be 4 billion years old, but it might be, dead, fossilized evidence, perhaps, of past life. So that's the storyline. That's what I specialize in, is looking at astronauts, trying to keep them healthy and well, and designing systems to counter these deleterious effects and try to improve their performance and motion. So here in the lab, I'll show you some videos of some of our simulators and some of the research that we do. I call one of them the Moonwalker. So here's one of my wonderful graduate students. He's just running on a treadmill. That's, of course, at 1 gravity level, Earth gravity. But now we're going to suspend him. Some of this work was done early with the collaborators here at Harvard, so we call that the Moonwalker. Now he's loaded for a 1/6 his weight, 1/6 gravity. That's on the moon. If you put him to Mars, it's 3/8. Let's just call it 1/3. Now, since spacesuits are $10, $20 million a pop, I don't have a lot of extra ones lying around my lab, so we build these carbon fiber legs and we dial in the stiffness. We dial in the same stiffness as you would feel in a big gas pressurized suit. But I'm taking energetics and looking at some of the measurements of how hard essentially it is to work in a suit. Have a little coaxing. How else can we study altered gravity? Because we can't get rid of gravity, so I go into underwater tanks. And I come up with these fancy systems. Now, this subject is on an instrumented treadmill, so I'm getting kind of biomechanical measurements, and is loaded, these black loading is loaded for a Martian simulation here. The first simulation was moon. This is lunar loping. Kind of looks like running. Now, we can really get lunar 1/6 gravity on an airplane. It's known as the vomit comet. And you go up to 40,000 feet and you dive like crazy. And here we can also get Martian locomotion. So now it's 3/8 gravity. This is true Martian gravity level on this airplane. Now, it's a great simulator. That's where we do a lot of experiments, but it does make you pretty nauseous. If you go for 0 gravity, you get about 20 seconds to take data. If you go for lunar gravity, you get about 30 seconds. Martian gravity, I get 45-second parabolas, but you get 40. And then you do a 2G pullout. It's like a bad carnival ride. And then you go back up over the top and you take data and you lose subjects and, and you hit the bag. There's rules about you have to hit the bag because you don't want that stuff flying around. So here's some of my team. Well, that's me. One-handed, see, microgravity is really absolutely very fun, very cool, because you get to fly, like a little one-handed, push-ups, easy. And here's one of my graduate students, Allie Anderson. She's testing out. It's blue in that picture. It's a black suit now. I'll tell you more about that. Here's a team, international team. There's my PhD student, Dustin Kendrick, team from King's College in London, and the European Space Agency, and they're flying on the Europeans' parabolic flight just last month. And we're looking at muscles and bones, and we're doing a lot of modeling to try to understand all this adaptation to these different gravity environments. So these are this black suit that's up here, if you can show it, we call it the gravity loading countermeasure suit. Now, it's for inside the vehicle. You're inside the vehicle. This one is actually for International Space Station. That black suit is our 5th version. It will fly in 2015, the fall of 2015, so just over a year. We'll fly this on a Danish astronaut. What are we doing? Well, we're trying to load him from the shoulders down to the feet. He's floating around in microgravity like my last size, but I want to reload so you feel one body weight loading on your feet. And then you just kind of go about your daily business, and if we can reload them during those activities, maybe we can prevent some of that muscle bone loss partially. And what else can we do? We really worry about spinal elongation. Almost all astronauts grow in space. That's cool, about 2 centimeters. I'd like to grow taller, but it's very painful. It's very significant back pain. So we're reloading someone for comfort, for performance, and for some of these effects. So this is called our gravity loading suit. I said here's students who are, again, flying up on that simulator, that microgravity simulator. Still tough to get one body weight loading for this suit, but we're working on it and keep improving the material properties and the design. Another use for this is our Earth applications. So in the lab, we do something called motion capture. We put a lot of sensors on people and we track their motion, track your walking, track your movement. So here you see someone walking down some stairs. I have 16 cameras and we're tracking a lot of dots on this person. It's a real person. This is a video of the real data. And what do you see here? Well, this is something called an IMU, an inertial measurement unit from the aviation world. But how I'm using it, there's data here, you see. This is a knee angle over time. This is an ankle angle over time. That's called kinematics, the body angles. How are the body angles moving? And we'd like people to move naturally and as well as they can. So we fly. These little sensors are just exactly the size of my watch. So I strap them on your body and I see how you're moving. And that's a pretty inexpensive system. And we'd like to replace the big $200,000 motion capture system that's in the labs, that's current state of the art. Why do I want to do that? Mostly for Earth applications, because this loading suit we think has great applications. One of the pathologies in particular is cerebral palsy, because you have different motor control, different movement. So this is a 6-year-old with cerebral palsy in a Russian version of this suit. We collaborate very closely with Russian colleagues at the Institute for Biomedical Problems, and they call this the Adeli suit for this. But you can see the bullets, and so we'd love to help enhance locomotion, especially when locomotion, you'd like to enhance it and get full range of motion and motor control. Improve the muscle tone if we can. So that's the next 10-year goal. Little suits for kids here on Earth. But back to space. This is the current state of the art of a spacesuit. Thank you for the introduction. All spacesuits that have ever flown have been gas pressurized vehicles. They're the world's smallest spacecraft. It's unbelievable engineering design. They're wonderful. They're marvels. Keep the astronauts alive. And they're pressurizing the astronaut to 1/3 of an atmosphere. We're all very happy here at 1 atmosphere. Lucky for us, because our life support system is pretty awesome here on Earth. We have to recreate that in the vacuum of space. But to keep someone alive, I only need to put 1/3 of an atmosphere of pressure on you. So how we do it now is put you in a gas pressurized balloon, keep you alive. We need pressure, we need thermal control, you need oxygen to breathe, you want to worry about humidity, all the things listed here. And the backpack, we call that the PLIS, or Portable Life Support System. That gives you your oxygen. It scrubs your carbon dioxide. All these, a little bit of humidity. Very important. That life support system is the most expensive part of the suit. As an astronaut, you see in the current spacesuit of NASA, here's training. We do a lot of training underwater, not just for research. Astronauts train 10 hours for each 1 hour that they're going to perform an EVA up in station. You might remember Apollo. That's Jack Schmitt.
Jack Schmitt.
So I like to show you Jack Schmitt is the only geologist scientist that we sent to the moon. And so we had a planetary suit, a locomotion planetary suit. Now, it wasn't great locomotion, but it sure was great for over 40 years ago. I think it was awesome. So that's what I'm interested in, is sending people back to the moon or Mars, and how can we make a very mobile spacesuit. This kept them alive, it did its job, but when we go back, keep fingers crossed, 50 years after that, hopefully not approaching 60, we should have a very, excellent and much enhanced engineering system that provides the mobility for the crew, because they're going there to explore. And again, you're going for a long time. You need to be very, very mobile. So this leads us to some of our ideas for the BioSuit, which I'll tell you a little bit about. But in compare and contrast, the current NASA suit is called the EMU, Extravehicular Mobility Unit. That's that gas pressurized suit. Provides 1/3 of an atmosphere. See up there, depends on what unit you want to use. 27 kilopascals, that's about 4.3 pounds per square inch. 1/3 of an atmosphere. And it's heavy. It's 140 kilos. Who wants to wear a 300-pound spacesuit? Well, it's okay for microgravity because you're floating around. But that's not okay. For the moon or Mars, you're going to get squished by your poor spacesuit. So that's a challenge, the mass, the weight of it, and the lack of mobility. So that's what we address in our research. And here you see an artist concept. Here you see the real spacesuit, the current NASA spacesuit, but it's in my lab. And again, I'm tracking how people perform in it. I'm tracking motion and angles. And then we have a smart robot. It's called M-Tall Chief. That's a quiz question. Why is my robot called M Tall Chief? I'll take the answer after we're done. We drive, the person moves around, replicating tasks, and then the robot moves around. Put the person in the spacesuit, move around, put the spacesuit on the robot, and it does the same motions. It has high precision optical encoders at the joints, and I can tell how hard you're working. You're using about 75% of your energy to overcome the suit, to move the suit. That's no good. I want you to get your work done and dig on the Martian surface. So I want all of your energy to go into your exploration, not overcoming the suit. So that's the big disadvantage of a non-mobile gas pressurized suit. So that's what we study. We'd like to change that. I'll show you a little bit more what we study. This is another quiz question. See if you know the artist and the name of the image on the left. You guys are so good. I ask this to my MIT students all the time, and sometimes I don't get answers. Okay, now, anyone know the on the right? I don't expect anyone to know that. That's one of my graduate students in Arizona in a spacesuit with a head tracker on, at nighttime. It's a nighttime spacewalk. It reminded me of the Duchamp. So now let's talk about engineering and design, and I'll tell you a little bit about some different projects. This one's actually really just come to fruition. So again, still the current state-of-the-art spacesuit. See some images here, but it's injuring the astronauts during training. We have 23 astronauts who have had major shoulder surgeries due to, the suit beating them up, unfortunately. So they're the right stuff, but you want to prevent that. So we study that. And I'll show you this picture here. It's called a hard upper torso. It's a fiberglass shell that's in the current suit. This is called a pivoted hut, and this is called a planar hut. It's a little hard to see here, but they're very different shoulder designs. We don't have injuries in the pivoted hut. You give someone their natural mobility in the shoulders, they do pretty well. Again, you're underwater, you're training inverted, you're upside down, you're training hours and hours and hours thinking about, repairing that Hubble Space Telescope. So it's really pretty hard work. The planar hut is the new only flight qualified hut. Planar, as the definition meaning, it's much more of a plane on my chest rather than a pivoted one. It's causing a lot of injuries. So we're studying that. We want to know what these hot spots are. Where in the suit, where's the suit beating me up, right? Where's the wear and tear of the suit? Kind of depicted there as hot spots. So I want to highlight the work of my most recent student, Dr. Allie Anderson. She's defended yesterday, so she's a very new doctor, just like our colleague who was introduced here. And this is in a collaboration with Harvard. So we want to map, no one's ever measured the human working in the suit, inside the suit. So I'll show you some pressure sensors. This is kind of the technology behind it. But we make these pressure sensors. I'll jump to show you a little bit of the details here. This is really Rob Wood's great work here at Harvard. So we collaborate with Rob and his folks. We make these sensors, show you them kind of in action, and then we've come up with the application in a suit. So she calls it the Polipo, because that is Italian for octopus. And so you see this sensor system here. So low pressures, what do I mean by low pressures? From 0 to 50 kilonewtons. So again, trying to map the human moving inside the suit, and then when I come in contact with the suit, can I measure that? Can I test those measurements? So then we put it into a shirt here, and we have all these sensors, these distributed sensors, very, very low profile. They're flexible, and they go all over the body. And that took a few years to do. We got the system up and running. And here it is at NASA. So that's Pierre Bertrand, my student. He's the videographer of the group. And Allie is the woman in there. So what we're doing, so we have this system. We actually have 3 sensor systems inside to map the performance. This suit that you see here is a gas pressurized suit. It's called the Mark III. It's NASA's most advanced prototype suit. demonstrating much better mobility than the EMU, than the one on space station, but much less mobility than we're trying to achieve through our designs. So that is the most mobile gas pressurized suit in the world today. And you still see it's semi-mobile, you know. You're not going to go run a 10K in there, right? Okay, so, you know, onboard sensing to map the person. Now what I'd like to do is show you a little bit of data. And so this is going to be an animation. Let me explain it before I'm going to run it. So these pressure sensors, as I said, they're all over the arms trying to look at the motion. And so you'll see the subject here in the Mark III. And there's going to be a little graphic here. And it's going to, yellow goes here. It's going to show you which sensor is kind of highlighting and where I'm interacting with the suit and then how I'm moving the suit. And you can see some pretty higher pressures up here, some peaks here. And then you can see when you do this motion, pretty much all the sensors are firing. We did simple joint motions. Okay, I'm flexing my arm, I'm extending. And then the kids will like this one. The students, this one where you go like this, a cross-body reach, they call that the reverse Macarena. So they do that. So you get all, you know, you get pretty good mobility out of that one. So let's see how the data looks here. So I'll stop. So, you know, across the body, can I reach my other hip? We take it for granted. You can reach your hip. That's a hard thing to do in a spacesuit. It's hard to get your hand out in front of you. So up, over. It's real hard to scratch your ear in a spacesuit. And you can see now, when I'm fully flexed and over here, you know, we're seeing pretty much interaction of the whole sensor system. So we map that, and we have, you know, a lot of data, but it's the first time that it's been mapped, kind of the human performance, moving the suit, if you will. So we're really excited to carry that system forward for spacesuit, gas pressurized spacesuit applications. So few definitions here for the BioSuit. Some people asked me when we got to see the suit in the beginning. It's called mechanical counterpressure. It's not a gas pressurized suit. There's no gas in the suit. There's gas for the helmet to breathe. You breathe there to stay alive. But the pressure, the 1/3 of an atmosphere pressure that I need to put on you to stay alive, the pressure component is here. It's a suit. It's mechanical pressure, mechanical counterpressure. It's pressing right on your skin. You have to do that constantly for, you know, 1/3 of an atmosphere. That's the trick. That's the design trick. But we think we can do it. It's technically feasible. I'll show you some of the data and tell you about how we think we can get there. And then, as I mentioned, all of our suit designs and our patterns and our custom suits always have applications here on Earth as well, biomedical applications here on Earth. This, in the background, is a big thing called an infographic, and it's a big poster I have in the lab. This is just part of it. It's too small to read, I know, but this is human history of spacewalks. So all these little dots, that's one. We do spacewalks just like you do diving with a buddy. So you go out of the craft. So here we are building International Space Station. We've done over 500 EVAs, spacewalks in human history. NASA, Russia, European, all of them. Here's Mars. I had to change scales. Just our first Mars mission, to go there and explore 600 days on the surface of Mars, that's over 1,000 spacewalks or EVAs. So we need a new suit. We need a different system. This is, I love the work of Dr. Paul Webb. This is called, we don't need the sound on this. It's low, that we won't be able to hear it. I'll just, yeah. If you can turn the sound down, that'd be great. It's NASA's designers saying they're reviewing this space activity suit. This is 1971. So Dr. Webb was a physiologist. I think he had a great idea. He's the first one that came up with maybe mechanical counterpressure. Since gas pressurized suits are so immobile, what if we pressurize the person? And he didn't have the materials that we have today. Matter of fact, spandex hadn't even been invented yet in the early 70s. So here's dressing on, he uses 6 layers of material in this space activity suit. And had great mobility, as you saw. You'll see the person just, you know, has really great mobility. The reason NASA didn't go forward with it and fund it is because you can't dress yourself. In spacesuit world, we call that donning and doffing. Putting on my clothes and taking them off. Donning and doffing. And it takes 2 people to help you get dressed in the morning. And you don't have those 2 buddies on Mars. And they definitely don't have enough time to help you get dressed. So we're kind of squeezing them in there. And it's tough. They get there, but, you know, it has to take some time. They're still trying to squeeze them in, zip up his seams, get his arms in there, and then you'll see a gas pressurized helmet go on, and that's very similar to this design. So again, mechanical counter pressure, pressure to the body, the suit body of it, and then with a gas pressurized helmet. So great idea before its time. So I really love the work of Dr. Paul Webb, and I'll tell you a little bit more about some of our patterning as well. So we have a serious exploration job to do ahead of us when we get to Mars. And so we'd like to design the system that makes sense to get us there. Oh, so this is just for fun. Now, Edna, I love little Edna, she's saying, darling, and it's fire retardant. The BioSuit is not fire retardant. We use polymers. It's kind of like a seersucker suit, right? So we've actually been working on this research longer than before the Incredibles came out. But I love that little shrink wrapped. You know, if I were a superhero, I'd be Elastigirl, right? 'Cause she has a cool suit. All of these are prototypes over the years. You know, really creative. You know, here's Paul Webb's suit. But there's been some really creative. So when you think of a spacesuit, don't just think of a white kind of Michelin man. There's been some really interesting research on prototypical suits. They haven't flown, but I think some of the best ideas come from some of the research and some of the prototypes. Kind of a hamster cage idea for before pre-Apollo, way back when. So I want to tell you a little bit about the design. And I'd like to give credit to Dr. Iberol. 1950s, but that was classified, and I wasn't quite born yet, and move up to 60s, to 70s. So he thought of patterning to try to get more mobility. What if we can, kind of looks like a Spider-Man suit? Well, again, we've been working on it before these Spider-Man movies came out. So you do the math. And what I'm showing you here in a cartoon is if you draw circles all over your skin, little infinitesimal circles, we blow them up here so you can see them. So draw circles all over your skin and move, because I want you to move just without any inhibition. That circle, if you draw that circle on your skin, it's going to move into an ellipse, right? It's going to transform into an ellipse like my cartoon up there. Well, those two red lines, they're really important. Those are two bisecting diameters. Now, we're three-dimensional creatures and kind of squishy and very complicated. But if you do the eigenvector three-dimensional analysis on this, voila, we get this wonderful pattern. So Iberol had this idea, and he did it kind of hand-drawing by geometry. But after working on it for a decade, now we have it mathematically derived. And so that's how, that's really important because these lines of non-extension, they're red on this suit. This is the MIT colored suit I had to bring just as a joke because I'm here at Harvard. There's white suits too, but I had to bring my MIT colored suit. So the red lines here are what you're looking at. They're red there. And so we basically look at kind of connecting the dots, if you will. So I call that a soft exoskeleton. So that's my internal structure. So again, I'm shrink wrapping you and putting the pressure, but that's how I can make a pressure suit with maximizing your mobility and movement through the arms and the legs. So that's what we attempt to do. This is work of colleagues at MIT. Well, how would you really make a shrink wrap suit? And what kind of polymers and materials would you have to use? Well, Greg Rutledge and Paula Hammond, you might know Paula's work from Spider Silk, is excellent work. Because see, I can say I know exactly what polymer and material. I want 40% stretch here, and I want 30% compression here. And so we have all this mapped out, but you can't go buy that material, you know, at the local fabric store. So we have to look at some really interesting materials, and they're coming along in development. And as soon as they produce them, I'll be the first user. So this is a technique called electrospinning, and it literally is spraying on in 3 dimensions polymers. Very, very interesting. So just to give you a little bit of a summary or highlights, when we design a suit like this, and our design partners, Trotty & Associates and Dainese, fabricates the mock-up so you can see it. So it's a lot of engineers at MIT working with designers, the aesthetics, give credit to Trotty & Associates and all our design friends. And so the mock-up that you see in front of you, it's a digital design. It's of me. We do a 3D laser scan, so we have a 3D body pattern. And this size right here is 340 meters. These red lines and black lines you see. Yeah, 3 football fields. It's kind of unbelievable. But that's 340 meters of patterning, of lines there that you see in the suit. And they tell me it's 140,000 stitches if you sew. You want to have an automatic machine driven by CAD when you do these things. And so what we're trying to do, we're maximizing mobility through the design and patterning and derive those, and then we're minimizing energy. So you choose the materials, you choose the pattern, and so that's the state that we're at right now for the BioSuit. To get it, and then we incorporate active materials, which I want to tell you a little bit more about. So the active materials, you might have heard of shape memory alloys, nickel titanium, sometimes in the press they're called muscle wires. They're pretty interesting. They can have two shapes. So first it was a little person shape. You heat it up, give it a little voltage. So you can have two shapes. See, now that's really cool for me. I don't think we'll have a whole suit, not a suit of armor for the astronauts where you have to shrink wrap the whole thing. But I really like this idea. As I was showing people at the beginning here, I really like this as kind of smart zippers. I put the suit on, but I have a little extra room, and then I kind of cinch it up. And actually our best candidate material right now is a shape memory alloy, this nickel titanium. So we make, remember Chinese finger traps you have when you're a kid and you got your fingers stuck in there? So we make them out of active materials. So it can open up, it can close, and we can actually get a lot of tension. Like get a lot of tension in those. So again, there's the making it kind of an active zipper, if you will, or an active band. The whole suit doesn't probably need to be made out of active materials. And here's a little bit more details in our latest paper, because this is current work. He graduated last week, and my second new doctor, Dr. Brad Holschuh, has been working on this problem with me for, we won't count, the last very many years. And great work, incorporating not just shape memory alloys, kind of the wires that you see here, but he's come up with a coil, a patented coil design. It's fantastic. We get a lot of force out of it. It stretches a lot, as you see here. Now it's really interesting, the colored, so we do kind of a tourniquet, which is what you see down here in the bottom. So I'll put passive elastic materials for most of the sleeve, but then the little coils right here, we're going to cinch those up. And he just nailed it. I told you in the very beginning we're trying to get 1/3 of an atmosphere pressure production. With passive elastic materials, things that you see here, we could get 20, 25%, but I was missing 5 to 10 kilopascals for the last decade, and we just nailed it with this great work. He can, and that's some data here to show you. If I want a 30 kilopascal suit, that's in blue. These are the material properties I have to do, and we do want the blue. These are just different. This is half that much pressure. This is more pressure. So now using this elastic fabrics, if you will, passive elastics is what they're called, and then the active materials, we can cinch it right up. So now we have a suit that produces more than sufficient, more than that 1/3. And it's the first time that actually we've been able to show this, except for at his defense last week. So it's a really great work. I'm really proud of him. So these active materials really they're quite wonderful. They've gotten us a long way. You see a helmet on here. That's actually a brand new helmet design. I said that is gas pressurized. You need to breathe air. And so just to show you a bit of an assembly, that's actually a picture of Allie, who I mentioned before. We're doing research, and that's a Google Glass. It's not as good as I'd like it to be because, we do a lot of traverse planning. I'll show you a picture in a minute. But right now, we can't put any of our real computer programs in Google Glass. I mean, you can take a picture of the audience or tell it to drive, which is very scary to get directions on something like that. But in our research, we still use desktops, but we have mission planning. What do I mean? Well, you want a map of Mars. If I'm the astronaut of the future is going to have a very smart system, very smart IT system in the helmet. 3D enhanced vision. If you want to take a look at the terrain, where am I going to analyze? What rocks should I pick up? So we do a lot of research to try to think. It's not just the helmet. It's kind of what are the smarts that you're going to build into the helmet system. And these are some of the smarts that we'd like to put into the helmet system. So if you want to be a Martian explorer, well, it's great terrain, right? Mount Everest? Yeah, pretty nice, pretty challenging. Beauty. Olympus Mons, now that's a mountain 3 times higher than Everest, right? If you go to the Grand Canyon on Earth, it's pretty impressive. It's lovely. It's wonderful, right? Nope. We have something on Mars called Valles Marineris. It would stretch across the entire United States. So Mars is extreme exploration. So we have to enable our explorers and our astronauts of the future. And it's not just explorers. It's just not astronauts that are explorers. I've been talking about astronauts because that's my specialty. But here's some maps that we play around with, and we send out astronauts on rovers, and robots. So it's a whole team of explorers. I'm there with my robots, I'm on rovers, because that's how you really explore. And everyone has capabilities and can take data, and I can make decisions. And so it's a whole team, it's a whole cadre. So we go out in the field and we practice and rehearse and we see how our systems are doing to see, can we really do this right? And practice here in analog field stations on Earth. And Earth has some interesting places, like way up in the Arctic, Idaho. It's not too remote. We'll be in Idaho this summer because the space science, the volcanic formations are fantastic in craters of the moon. And we're there as a support team to kind of simulate what the astronauts would be doing, because it's not shirt sleeve science. I got to strap on suits and heavy suits and say, your work's going to be really much harder. Okay. Then coming to the end here, to leave plenty of time for questions, one of my biggest thrills has actually been the publicity and the press we've gotten, unintentional. I'm a researcher, pointy-headed academic, and we're trying to do the best we can. But the BioSuit's gotten a lot of press. And the fantastic part about that is for all of you young kids in the audience. It's great for our older folks too, and welcome. But if I can get kids excited about exploration in space and really just about education in general. I don't call it STEM education, I actually call it STEAM. I put the arts in there because I need everybody. I need everyone to study science, technology, engineering, arts, and math, because all I know is we have some big challenges. Some of them are maybe exploring distant planets, but there's a lot of engineering challenges I have right here on Earth as well. So I'm here to recruit all the young people, and they think, space is cool, and spacesuits are cool, and design is cool. That's been really fun. And we run Wallace and Gromit. I don't know if you're claymation fans, just in this side. So I'm happy ever since, right? I love claymation. I love Wallace and Gromit. So it's really fun to, I've watched all the claymations, right? It takes us 10, 15 years or more of research to design a Mars spacesuit, but it takes them years, and they're really small. If you meet Wallace and Gromit, they're only this big. They're real small. I think this is actually my slide. So where's a little view of the future, if you will, looking out. These are, as an engineer, we look for technologies, we develop some of them, we pay attention to what else is there. So it's kind of my list of things we're looking at right now. We call it reconfigurable hybrid humans. What does that mean? Well, we're at a point, I think, in some of our designs where the human capabilities and performance and then the machine, if you will, or the augmented performance, we just work in parallel. We just work right together. So that's what we mean by this concept of hybrid humans. Superhuman performance, how high can a person really jump? We know about professional athletes, but how high can I jump? If I put some, kangaroo springs on with technology, maybe I can slam dunk a basketball. I was a basketball player in college, and you can see I'm challenged vertically. So I still have the dream. I have to make myself some springs so that I can slam dunk. And we're working very hard. Again, our BioSuit is essentially a soft exoskeleton with active materials. We're pushing in those directions for the research and for the research of the future. I want to leave you with this images. I'm not sure if you've seen it. I hope you jump on YouTube after this. This is taken from a recent International Space Station mission. It's sped up, but on Space Station we orbit the Earth every 90 minutes. You do one lap around the Earth. So the view from space, back to my opening remark to Bucky Fuller, is really quite spectacular. The glow that you see there, it's a fast pass over the U.S. You might recognize some of the topography. Again, space station is only 200 miles up, so beautiful view. And this is our life support system. A little blue faint line on the horizon. That's our atmosphere. That's Earth's entire life support system. If Earth is the size of a basketball, our life support system's 3 human hairs. And this is not colorized. This is not a colorized image. That's what it looks like from Space Station. That is the true auroras, the southern lights. Again, looking very closely there at the atmosphere and the beauty. It's very, very beautiful to fly over Earth and see. You see human presence everywhere, of course. Good place to see clouds and storms and monitor, of course, Earth observations from space. These are solar panels. There you go. You can tell where we are. I'll be on a plane momentarily, right there. That nice bright spot. I have to be in Milan tomorrow. So I leave you with that image. I think it's a beautiful image of Earth. We call it Spaceship Earth. That was coined by Buckminster Fuller. We're all in this together. I'm just glad to be able to do such exciting research and kind of look at it and do my part, but it's really for all of us, and our decisions are really important. So think again, our space research helps us reflect on Earth and think about our humanity. So I appreciate your attention. I'm more than glad to, I think we have plenty of time for questions.
Thank you, Dava. We will now, thank you so much.
Absolutely.
We will take questions. We will go back and forth across the room, so one side doesn't get to ask all the questions because it appears this side already. I've seen arms and arms and arms. We'll start in the front and we'll go back.
I'm curious to know, are there different suits for men and women?
Yes, and if you wouldn't mind telling me your name, I enjoy.
Oh, Shirley.
Shirley, nice to meet you. So, yeah, it's a 3D, our suits are 3D form. So, people ask me, it's one of our claims to fame. One of the NASA administrators said, when I can tell the difference in genders on a spacesuit, that's a good thing. So, you can't in the current suit, right? So yes, it's a female or male form, but it's just your unique form. Because you said from a laser scan of your body. So it maps custom. You, it's custom. They are all 100%. It only takes us 30 seconds to do a full body laser scan. So that's the easy part, is the laser scan. You can go to Brooks Brothers in New York.
Question.
Get your suit out.
Is the stitching customized per person too?
Is the stitching customized? I'm going to repeat it so the people in the other room can hear us. Is the stitching customized per person also?
Yes and no. Yes, the part is that the patterning comes, we scan you, so I know your body, and then this kind of mathematical analysis that I showed pictures of, that's that done, and then does it scale, but you get your own. So everyone's going to be kind of the same. These red lines are going to be in the same way, if you will. The $20 million question that we haven't answered yet in our research is that patterning follow the musculature? And is that how skin collagen is really laid down? How biologically relevant is it? That would be a big breakthrough. But right now, we do the patterning and the design and the mathematical analysis to get that.
Question up above.
We do parallel to the mechanical pressure on the body. We do some physiological preparation of the astronaut, like shepherds. They're able to go on Everest in the low pressure already. So we can train the astronaut in the same way.
It only works till about 5 or 10% loss of Earth atmosphere. Yeah, so we can't get the majority of the way there. Human physiology is fantastic, so high mountain climbing, but that gets us just a little ways there. It's a lot less pressure. Yes. It's a lot less pressure when we go to a vacuum of space. Mars has an atmosphere, but it's 1% of Earth. So we still have to repressurize. So we can't train the human body to exist in a vacuum of space. It wouldn't work.
Question right here.
You lost me when you were talking about the black suit and you called it a loading suit. What do you mean by that?
What is a loading suit?
Great, thanks for the question.
Weight, are you?
So it's called we call it the big long name is the Gravity Loading Countermeasure Suit. All NASA projects have to have an acronym, I apologize. But what it is, gravity loading, this is for microgravity, for space station. So you're floating around, right? You're unloaded, it's really fantastic, but the problem about the muscle and the bones. So I'd like to reload you while you're in microgravity. So how we do it now is the exercise. The astronauts get on a big treadmill, they also they become power lifters.
Right.
Put a bungee on, and I have to lift weights, essentially, on space station. Our suit design is, I'm going to reload you. So typically I'd be floating around. I'm going to have the equivalent. Feels kind of like someone pushing on your shoulders, but I'm just going to load you in one dimension for this suit, down to your soles of your feet. So from
heavy.
here.
It's heavy.
No, it's really light.
So how does that do?
There. So. It's my size, so it won't quite fit you. But it has to be comfortable because you're going to feel a lot of weight on your shoulders, right? And you're going to It's really good. It'd be really good for guys to do this. You know, my students are man and female, right? Because it's just like putting on stockings, and all of us ladies know how to put on stockings. So you climb into this baby, see, and you put it in, and it's, you know, it's pretty tight, but you can don it. You can put it on yourself. And then I dial in the material properties. We make this material different. Why are these white lines on it? Because I'm measuring how much tension. It's pulling tension from your shoulders. See, the shoulders are not extensible. This material doesn't move. And I put it on here, and it's too short, and I crank up those stirrups.
Okay.
So it's just like kind of wearing a leotard, but I'm compressing you. And I said, first and foremost, we're trying to take care of a spinal elongation compression. That's a couple centimeters. So I'm putting this on your shoulders and kind of crank it down. Now, if you wear this, if we can make it comfortable enough, and you wear it and you're floating around all day while you're in a space station, it's kind of in parallel to other exercises. We're trying to think about how it can help the musculoskeletal system. Does that make sense?
Yes,
You got it? And then the other thing I should show you about here, since we're close up here, see these black, these ribbons, call it arrestor ribbons, right? Because I know how much I want it to stretch. So you put it on an urge, you stretch it like that. See that? And they're going to stop it from stretching anymore. So this is stretchy material. It's all black, so it's a little hard to see, right? And then that arrests it. So kind of dial in the longitudinal amount of stretching that I want the suit to impose on you. And you're going to feel it. You have to wear hard-soled shoes. Carbon fiber soles is what we use, because it's going to be equivalent of one body weight. 700 newtons, 550 newtons, whatever you are, 100 pounds to 200-pound people. So you're going to have that loading through your soles, all the way down, all the way down the
Question
bottom.
from up above.
I was wondering, for the suit, you said that it's one suit for one body. But what happens if you have a long mission and maybe you can lose weight or gain weight, or you know, your body might change?
Right.
So how
It does a little bit, and people
Let me
up to...
repeat for the other room. What happens
you.
on a long mission if you start losing or changing your weight? Will your body suit still fit you?
Yeah, so we think we can take about 5% variability, you know, but you want to stay, you know, can't gain and lose too much. And it turns out a lot of astronauts actually do lose some weight, you know, because you don't have so much fast food up there, right? You don't eat too much, you're working hard. And you have a totally redistribution of your fluids in space. So all astronauts get chicken legs. You go up there and you're going to have a big fluid shift. It's the plasma shift. And you're going to excrete at least a liter of fluid. And then you get puffy faces, because here's my heart, here's this. So now the fluids are kind of circulating more here. You're fine. I mean, your blood, you know, still pumping to your toes up. But you have this big, massive fluid shift, excrete liquid. So we call it puffy faces. Kind of looks like they have sinuses. And they're, you know, their legs look a little skinnier. So we take into account that type of variability. But that really is over your whole anthropometry. That's less than 5%. That's a few percent change. So our designs take into account a few percent change.
Your backbone stretches also. You gain a little bit of height.
2 centimeters. The
2
backbone's
centimeters.
pretty significant. When you're unloaded for microgravity, now when we get back to Moon and Mars, we don't know. I mean, we've been there, but we didn't take any measurements on the back. So, but we're in a gravity field, but it's a low gravity field. Are we going to have any spinal elongation or not? We don't know. But microgravity, we do see significant spinal elongation.
One of the things that the shuttle pilots had to watch out, the astronauts, is when they were up there and they let their suits out, tightened them up, and they came in for landing, they forgot to tighten them. The suit's killing me. Young man right there, question.
How long can you stay outside in the suit?
So
how long can you stay outside?
Yeah, how long? So this suit, you stay inside, right? Because your arms are hanging out there. This suit is the EVA, the spacesuit to go out to for outside. So we're designing right now. The current NASA suit, they go at 8 hours would be really long. 6 hours, but you have to work. They have to work hard up there. So 6 hours is a typical spacewalk to 7 hours. 8 hours is as far as we push it. The world record's 9 hours, and that was a special case. So 8 hours, because then we don't have any more oxygen to breathe. So you have to go back into your spaceship. So you have to recharge. So this one, I'm actually designing it right now in the vacuum chambers. We test it for hours, but we test it for like 2 to 4 hours, because I think you're going to want to come in and get some lunch, and you could go back out for another 4 hours or something. And it helps us with how much oxygen I have to give you. So if I give you a suit and you go out there in the morning and do your work, I can have much smaller canisters. Come in, get some lunch if you want to, and then send you back out for another 4 hours. And you have to go again the
Question
next
over here,
day and the
please.
next day. So just about 8 hours a day of work, but you need to keep going out.
Question
help?
over here.
Can you talk about the technology that you're doing for the hands? Because all of the old imagery, the hands are so bulky. And
Yeah, it's a great question about the hands and glove design. So we actually have a new glove project right now. We haven't worked much on gloves in the future. We kind of divided up different university partners. So we've concentrated on the suit, especially the BioSuit for mechanical counterpressure. There are some mechanical counterpressure gloves that had been designed out of the University of California, San Diego. And as you might imagine, they're tight and fitting. They're pretty darn mobile. The hand, my degrees of freedom in my hand, right here, it's phenomenal. It's truly phenomenal. So it's almost as hard to design a glove as it is a whole suit with the amount of mobility that you want to impart. And if you go back to the Apollo bloopers, I call those, falling down, that is the #1 complaint by far. What's wrong with spacesuits? Terrible gloves. Give me hand mobility. Injuries, I told you about how we're studying injuries. We study shoulder injuries and we're mapping. Well, we've already studied hand injuries. It's all nail delamination, fingernails fall off, things like that. It's not so, it's like running the marathon, your toenails fall off, but it's excessive. So we do not have good mobile gloves.
Question way in the back, the lady in black.
Yeah, thank you. I wonder, the suit over there is very thin. I wonder, can the astronauts in the suit stay in the space and they don't feel coldness? I think probably you have thicker coats for the astronauts.
Right. So, So yeah. So I can read. So the question is, does it also give me thermal control? How is the astronaut going to get really cold because this is really thin material? So yes, we're trying to make it as thin as possible because that's again how I give you maximum mobility. So this is a pressure layer. This is the pressure layer of the suit. It turns out that we've already tested these black lines here. They're gold in some other prototypes, like pictures you might have seen. We can give you thermal comfort, about 10 degrees comfort. That's what we do in this BioSuit. And then you're going to wear an overcoat, really a space overcoat, because you have to keep warm at plus or minus 200 degrees C, depending if you're on the moon or you go to Mars. But it's quite a large temperature range, hundreds of degrees Celsius or Fahrenheit at that level that you have to control for. But we don't do that in the pressure layer. As soon as you do that, like in the current design, you limit mobility. So one's a pressure layer, try to maximize the mobility, and then you put a thermal coat on. The good thing is that technology is pretty much here. I mean, we explore in Antarctica. It's cold, not quite to 100-degree variability, but the thermal control problem is we have a handle on that. But again, I decouple it in terms of the design. Thanks for the question.
We'll take 2 more questions, and then I think she may have to dash for her taxi cab. So this gentleman will take one right here.
How is the loading suit effective on, for example, a child with cerebral palsy?
So this loading suit, so it makes sense.
How is this suit effective for children with cerebral palsy?
Thank you. So it's it's like think of it as a bungee suit, if you will. Kind of that's actually the Russian design is literally uses bungee cords. We try to make it more comfortable, but with the elasticity of the material. So it's pulling down on you, if you will, and then we make it small. We sense what's your leg motion. We're looking at muscle tone, so muscle tone and range of motion and things like that. And depends what pathology you take, but say for instance in cerebral palsy. The muscles really stiffen. I know I'm no expert in cerebral palsy, but we have very nice experts in Boston who tell me, about the disease itself. We can't cure the disease. We want to make an enhanced locomotion environment for some folks. And so we think about range of motion and muscle tone and kind of think about it as a kind of a supportive system, but also allowing you full range of motion. And like I said, that's the next 10-year project, so we have more work to do for sure. Is that Adeli suit that I showed, that I mentioned was a Russian suit, that is a commercially available product in Europe for CP therapy. You get people moving their arms and legs, and it's kind of like a workout suit. You're kind of moving against some of the resistance, but you want to get full motion, and then you want to be moving and exercising the legs or arms or the muscles. Does that answer your question?
Another question up front here.
I'm curious, two things. One is, it sort of ties on to the musculature. How much physiology, obviously, goes into this, and how deeply do you go into, say, musculature? And the second part of the question is about astrobiology, and where does that fit into this, living in extreme environments?
Okay, great question. So how much physiology and how much astrobiology? So for an aerospace engineer, I know way too much about the skin. I mean, we didn't set on it. I always wanted to study astronaut performance in humans, but I'm an aerospace engineer, so I use, control theory and dynamics and model the human and things like that. But we took a deep dive, and it became fascinating, and we just kind of kept diving and patterning, and now we have, I didn't show you our latest data there, but for the patterning, now we can measure the pattern about 1 millimeter accuracy now on my skin maps. And then in the engineering part of it that I understand, that strain and stress, and I think, oh, what material will give me a second skin? I call this BioSuit a second skin design. This is one beautiful organ. What a design. Master designer, if I could just replicate skin. It's pretty amazing. So again, like I say, but from an aerospace engineer, the graduate course I teach is space biomedical engineering. So it's quantitative physiology. I don't do anything at the cellular or molecular level. That's for other folks. As an engineer, I kind of use engineering tools and research approximation and delve into quantitative physiology. I study whole body performance. And then your other one, astrobiology, is great. I'm fascinated by it. That's not my expertise at all. But we team up. Right? I have fantastic...
The reason I ask that is there any applications for this for deep sea?
Well, deep sea, I'm a scuba diver as well. I mean, exploration to me is space and sea, so I don't...
astrobiology I meant because the deep sea vents are extreme environments.
But yes. So, yes, I do have a very new funded Navy project, because guess what? They told me, hey, it's like a man in a can, they call it. They're in a big robotic can, and they have no mobility. Well, you'd like to be swimming down there. Now, so the mobility aspect and designs probably work. The pressure production, see, space, it's a vacuum, so I need to pressurize you. In deep sea, you have plenty of pressure. The problem is when you come up and you don't have enough pressure. So we don't need pressure garments, but we do need the, I think, kind of second skin mobility type of systems have really, hopefully, fascinating undersea applications. So we're taking a look at that right now.
I'd like to thank Dava Newman. Thank you for joining. I have a question.